Hello everyone and welcome to the coronavirus edition of the 9th lecture of our signal theory class. In this lecture we will conclude the Laplace transform and the Z-transform. I will show you block diagrams of systems and we will learn some basics about the state space representation of systems. First, let's summarize the system description that we had thus far. We have learned that in time domain the continuous time systems can be described using a differential equation and discrete time systems can be described using a difference equation. The continuous time systems can be analyzed using the Laplace transform, this is its definition, and the discrete time systems can be analyzed using the Z-transform. This is the Z-transform definition. When you apply the Laplace transform to this differential equation and assume zero initial conditions, you will get this equation. And when you apply the Z-transform to this difference equation and assume zero initial conditions, you will get this equation. Now from these two equations, you can get the transfer function. In the continuous time domain, the transfer function is the function with which you need to multiply the Laplace image of the input signal to get the Laplace image of the output signal. Also, you can define it as the ratio of the Laplace image of the output signal and the Laplace image of the input signal. If your system is described by a differential equation like this one, the transfer function will look like this. These a and b coefficients in the differential equation will be these a and b coefficients in the transfer function. For discrete time, the transfer function is the function with which you need to multiply the z image of the input signal to get the z image of the output signal. Also, you can define it as a ratio of the z image of the output signal and the z image of the input signal. If your system is described by a differential equation like this one, the transfer function will look like this or this. You can express it with negative powers of z or positive powers of z. These a and b coefficients in the difference equation will be these a and b coefficients in the transfer function. Now, a continuous time system will be stable if the poles of the transfer function have negative real part, that is, they lie in the left-hand side of the complex plane. The discrete time system will be stable if the poles of the transfer function have their absolute values less than 1, that is, they lie inside a unit circle. If only one pole gets to this right-hand side or outside this unit circle, the system will be unstable. To describe the system, we can also use the frequency characteristic. With continuous time systems, when you substitute j omega for s in the transfer function, you will get the frequency characteristic. And if this is the Fourier spectrum of the input and this is the Fourier spectrum of the output, then the relationship between these two spectra is given by the frequency characteristic. When you multiply the spectrum of the input signal with the frequency characteristic, you will get the spectrum of the output signal. For the discrete time systems, you will get the frequency characteristic when in the transfer function you will substitute e to the j omega for z. And if this is the Fourier spectrum of the input signal and this is the Fourier spectrum of the output signal, then the spectrum of the output signal can be computed from the spectrum of the input signal by multiplying it with the frequency characteristic. These formulas give you a guideline how to compute the output of a system if you know the input and the frequency characteristic. You can compute the input spectrum, multiply it with the frequency characteristic, and then compute the inverse Fourier transform of the output spectrum to get the output in the time domain. We did this and we called it filtering in the spectral domain. In discrete time, this computation can be actually performed to process your signals. However, in continuous time, it is merely an abstraction that allows you to describe and understand the behavior of your system. In reality, a continuous time system will process the input signal by passing it through some resistors, capacitors, or inductors, or some other elements. Now, in the time domain, you can compute the output of your system using the convolution of the input signal with the impulse response, where the impulse response is the response of a system to the Dirac delta function. This goes both for time continuous and discrete time systems, even though the definitions of the convolution are a bit different. And these are the relationships between the impulse response, the transfer function, and the frequency characteristic. In continuous time, the Laplace transform of the impulse response is the transfer function, and the Fourier transform of the impulse response is the frequency characteristic. In discrete time, the Z transform of the impulse response is the transfer function, and the frequency characteristic is still the Fourier transform of the impulse response. Here you have a different view. When you have a system, in the time domain you can describe it by an impulse response, and the output is given as the convolution of the input and the impulse response. To this you can apply the Fourier transform, and then your system is described by the frequency characteristic, and the output spectrum is given as the multiplication of the frequency characteristic and the input spectrum. Or, with time-continuous systems, you can do this in the Laplace domain, in which case the system is described by its transfer function, and the Laplace image of the output is given as the product of the transfer function and the Laplace image of the input. With the discrete time systems, you have the same things, except with the Z transform. Now, there are some limitations. The individual transforms have to exist, which for the Fourier transform is rather a limiting condition, and the Laplace transform and the Z transform are looking at the signals only for positive time. Here I have some extra properties for both the Laplace transform and the Z transform that we did not need on the previous lectures, so I did not want you to overload you by unnecessary formulas. What I want to add in this lecture is this. On the previous slide, you have hopefully noticed that when I have the convolution in the time domain, in the Laplace domain, I'm multiplying the Laplace images. So similarly to the Fourier transform, the Laplace transform turns the convolution into the multiplication. And the same goes for the Z transform. It turns the convolution into the multiplication. In this derivation, I show you what is the Laplace transform of this integral function of signal x. Here I have substituted into the definition integral, and I will evaluate it by parts. I will integrate this exponential, and I will differentiate this integral function. Here I have integrated the exponential, and I have copied the integral function. Here I copied this integral of the exponential and take derivative of this integral, which is just x of t. Now, when time goes to infinity and the real part of s is positive, this exponential goes to 0, and unless this is some really extreme function, this entire expression will be 0. When time is 0, this integral is 0, so this entire expression is 0. So this expression is 0 for both these limits. In this expression, I can take this minus s in front of the integral, and what I'm left with is this. This is just the Laplace transform of x. So when I take the Laplace transform of the integral of my signal, in the Laplace domain, this will be converted into the division by s. Recall that the derivative in the time domain causes multiplication by s in the Laplace domain. Now you know that the integration in the time domain causes the division by s in the Laplace domain. In this derivation, I come back to the time shift in the discrete time. Before we had only a time delay. Here I assume that this m is positive, so I have time shift forward in discrete time. The formula for the forward time shift is quite similar to the formula for the time delay, but the derivation has a tiny difference. Here I have substituted into the definition of the Z transform, and I will make this substitution, which will give me this. Here I can split this expression into these two expressions, and I can take this z to the power of m in front of the sum. Now, if I assume that my signal is 0 for the first m samples, then I can rewrite this expression like this, where this is just a z transform of an unshifted signal. So, if the first m samples of my signal are 0, then this positive time shift will cause multiplication by z to the power of positive m in the z domain. Now, here I have two formulas that you will use, for example, if you will continue to study some control theory. Both these formulas can be derived from the expression for the Laplace transform of the derivative, which is this. Let's take a look at what happens when I take this expression and I take a limit with s going to infinity and I apply that limit to both right hand side and left hand side. On the left hand side I will have this. Here if s goes to infinity, this exponential will go to 0 for any positive time, therefore this integral will be 0. On the right hand side I will have this limit, and this limit is supposed to be equal to this limit, which is 0. Consequently, the limit of this expression is this initial value of the signal. We call this formula the initial value theorem. Now let's take a look what happens when I take this expression and I take a limit with s going to 0. On the left hand side I will have this. If s goes to 0, this exponential will be 1 and this integral will become this one, which is this. This means the limit of your signal when time goes to infinity. Now on the right hand side I have this limit. If these two things are equal, I get this. This formula is called the final value theorem. We will not utilize this initial and final value theorems in this class, but some of your teachers may use it in their classes, so I suggest that you familiarize yourself with these theorems. Another addition to the system description are block diagrams or schematics. We already had some schematics of discrete systems in the time domain. Now we will take a look at what we will get in the z domain. Here I have a difference equation of a second order system. The u is the input and y is the output. When I apply the z transform to this difference equation and I assume 0 initial conditions, I will get this. Now I will take these terms and put them to the right hand side of the equation. Now I can use this equation to draw the schematic. Let's see what we have here. I'm supposed to take the z image of the input signal, this u of z, and multiply it by b0. And that is what I do here. Here I have my u of z and multiply it by b0. Next, I'm supposed to take u of z, multiply it by z to the minus 1 and by b1. So here I take u of z, multiply it by z to the minus 1 and by b1. Next, I'm supposed to take u of z and multiply it by z to the minus 2 and by b2. So here I have u of z multiplied by z to the minus 1 once. Here I will multiply it again, which will give me u of z multiplied by z to the minus 2, and then I will multiply it by b2, as I was required to. Next, I need to take the z image of the output signal, which is y of z, and multiply it by z to the minus 1 and by minus a1. So here I take y of z multiplied by z to the minus 1 and by minus a1. Next, I'm supposed to take y of z multiplied by z to the minus 2 and by minus a2. So here I have y of z multiplied by z to the minus 1 once, and here I will multiply it again, which will give me y of z multiplied by z to the minus 2, and that I will multiply it by minus a2. Last, I'm supposed to add everything up. So I add everything up. And when I add everything up, I should get a0 times y of z. So at this point, I should get a0 times y of z. Now, what do I need to do to get y of z from this? This is what I need to do. I need to divide by a0. So this is how you draw your schematic. This form of the schematic or block diagram we call the direct form 1. And we already had this in the time domain, and we saw this form. And you can see that this form has the same structure as this one, except in the time domain I will just have signals instead of z images, and I will have time delays instead of multiplication by z to the minus 1. Now I can turn the schematic in this form into the schematic in this form with the trick that we used in lecture 4. I need to realize that this system, this filter, is actually composed of two filters. This would be the first filter and this would be the second filter. Now it doesn't matter in which order I will apply these two filters to the input signal. It doesn't matter whether I first multiply by the transfer function of this filter and then by the transfer function of this filter. I will get the same result when I multiply first by the transfer function of this filter and then by the transfer function of this filter. The multiplication is commutative. So I can change the order of these two filters. I can first apply this filter like this and then this filter like this, which will give me this structure. And here I need to realize that if these two values are the same, then these two values are going to be the same and these two values are going to be the same. So I can combine this into this, and that will give me this form of the schematic, which we call the direct form 2. And this is the time domain equivalent which we had on lecture 4. On this slide, I will show you yet another form in which you can draw the schematic of a discrete system. In this derivation, the first 3 lines are the same as on the previous slide. This is just the difference equation of a second-order discrete system. This is what you get when you apply the z-transform, and this is what you get when you take these two terms and put them to the right-hand side. Now, on this line, I have collected all the terms that were multiplied by the same power of z. So here I have collected the terms that were multiplied by z to the minus 1, and here I have collected the terms that were multiplied by z to the minus 2. Now, I will take this expression, once more, this expression, and I will put it into bracket like this, and I will multiply this bracket by z to the minus 1. When I do that, here I need to multiply only by z to the minus 1 instead of this z to the minus 2. Now I can use this equation to draw that different form of the schematic. So let's see what we have here. I need to take u of z, which is the z image of the input signal, and multiply it by b2, plus I need to take y of z, which is the z image of the output signal, and multiplied by minus a2. And that is what I have here. I take u of z multiplied by b2 plus I take y of z and multiplied by minus a2. Now I need to multiply this expression by z to the minus 1. Here I multiply by z to the minus 1, and that will give me this v sub 0 of z, that is this expression. Now I need to take u of z multiplied by b1 plus I need to take y of z and multiply it by minus a1. So I take u of z multiplied by b1 plus I take y of z and multiply it by minus a1. Then I need to multiply by this z to the minus 1, which I have here, and that will give me this v sub 1 of z, which is this expression. Next, I need to take u of z and multiply it by b0. I take u of z and multiply it by b0. Last, I need to add this term plus this v sub 1 of z, and that is what I do here. When I do this addition, I will get a0 times y of z. That is what I get at this point. Now to get this y of z from this a0 times y of z, I need to divide by a0, which is what I have here. So this is how you can draw that alternative form of the schematic of a discrete system, and this form we call the transposed direct form 2. This is the equivalent in the time domain. Again, the structure is the same, except instead of z images, you have the time domain signals, and instead of multiplication by z to the minus 1, you have time delays. And now we have to do the same thing for the time continuous systems. So here I have the differential equation of a second order system. Now I can apply the Laplace transform to this differential equation, and when I assume zero initial conditions, I will get this. I could proceed with this equation and draw a schematic in which I would have multiplications by s. However, this is not how it is usually done. The problem is that the multiplication by s is equivalent to a derivative, and when continuous time systems are simulated in a computer, for example in the Simulink, the derivative does not have favorable numerical properties. It turns out that those simulations work a lot better when instead of derivatives we use integrations. And switching from derivatives to integrations in the Laplace domain is quite easy. All I need to do is to divide this equation by the highest power of s, which in this case of the second order system is s squared. So when I divide this equation by s squared, I will get this form in which I have divisions by s, and divisions by s correspond to integration. Now, similarly to the previous cases, I will take these terms and put them to the right hand side. And now I will proceed to draw the schematic using this equation. So again, what do we have here? We have u of s multiplied by b2, so here I have u of s multiplied by b2. Then I have u of s divided by s times b1. So u of s I need to divide by s and multiply by b1. Here I have u of s divided by s squared and multiplied by b2. So here I will take u of s, which is already divided by s, I will divide it by s again, and I will get u of s divided by s squared, which I need to multiply by this b2. Next, I need to take this y of s divided by s and multiplied by minus a1. So I take y of s divided by s and multiplied by minus a1. And here I need to take y of s divided by s squared and multiply it by minus a0. So here I have y of s, which is already divided by s. I will divide it by s again. That will give me y of s divided by s squared, and I will multiply that by minus a0. Last, I need to add everything together, which is what I'm doing here. And when I add everything together, I will get a2 times y of s. At this point, I will get a2 times y of s. And this expression I need to divide by a2, which will give me y of s. So this is how you can draw a schematic of a continuous time system. Except this form is not used very often. Instead, we use the same trick which we used before. We can recognize that this system can be split into these two systems, and we can switch the order in which these two systems are applied. We can use this. And here we can realize that when these two values are the same, then these two values are the same, and these two values are the same. So you can combine this into this, which will give you this form of the schematic of a continuous time system, and this form we call controllable canonical form. This is the time domain equivalent. Again, instead of the Laplace images of the input and output signal, you have the time domain signals, and instead of division by s, you will have integration. On this slide, I will show you an alternative form in which you can draw a schematic of a time continuous system. In this derivation, these first 4 steps are the same as the ones of the previous slide. Here I have the differential equation of the system. Here I apply the Laplace transform. Here I divide by the highest power of s, so that I have only divisions by s in this equation. And here I take these terms and put them to the right hand side. Now on this line, I'm grouping all the terms that are divided by the same power of s. This term and this term are divided by s to the power of 1. This term and this term are divided by the s to the power of 2. Now I will rearrange these two terms into this form where I divide this term by power of s and both these terms by s. And once again, I will take this equation and use it to draw the schematic. So what do I have here? U of s times b0 plus y of s times minus a0. And that is what I draw here. U of s times b0 plus y of s times minus a0. Now I need to take this and divide it by s. That is what I have here. To this, I need to add u of s times b1 plus y of s minus a1. And that is what I have here. U of s times b1 plus y of s times minus a1. Now I need to take the result of this and divide it by s. That is what I have here. And to this, I need to add b2 times u of s. b2 times u of s is added here. And when I add everything together, at this point I will get a2 times y of s, which I need to divide by a2, which will give me y of s. So this is how you can draw this alternative form of the schematic of your time continuous system, and this form we call the observable canonical form. This is the time domain equivalent. As before, instead of these Laplace images of the input and output, you have the time domain signal at the input and at the output, and instead of division by s, you have this integration. Let's talk a bit about the state space representation. The state space representation is actually something that we have used very briefly without talking about it. We had this example with a ball on a spring, where the ball had some position P, mass m, and the spring had some stiffness K. This net force acting on the ball, this capital F, was expressed as negative stiffness times the position of the ball minus some coefficient of friction times the velocity of the ball plus some external force acting on the ball. That external force could be me pushing on the ball. The acceleration of the ball was expressed as the net force divided by the mass of the ball, which gives you this. To describe the movement of the ball, we needed to add that the derivative of the velocity is acceleration and derivative of position is velocity. Now you can substitute this equation into this one, which will give you these two first-order differential equations. From here, we proceeded to substitute this equation into this one, which gave us this second-order differential equation, which we then use to find the function p of t that described the position of the ball in time. So we already had these equations. What we will learn in this lecture is that this second-order differential equation we call the input-output representation, and this system of the first-order differential equations we call the state space representation. What is the difference and why do we use this terminology? The input-output representation is a single, typically higher-order differential equation that shows the relationship between the output and the input of the system. For example, in the case of this ball on a spring, we can consider the external force to be the input of the system and the position of the ball to be the output of the system. And this input-output representation would tell us how they are related. The state space representation is a set of first-order differential equations that do not only describe the relationship between the output and the input of the system, but they also describe the development of the state of the system. What do I mean by the state of the system? The state is a set of values that can tell you enough about the system to predict its future behavior. In the case of this ball on the spring, to be able to predict what the ball will do, I need to know where it is and what is its velocity. Also, I need to know what are the external forces, but the external influences we do not include into the state of the system. When I know what is the position of the ball, what is its velocity, and what are the external forces, I can use these equations, which will tell me how the state of the system will change. That is, how the velocity will change and how the position will change. And of course, the rate of change is expressed as the derivative of the velocity and the position. So using the state space representation, you can take the state of your system, and from this state you can compute how the state of the system will change. And from this you can compute the behavior of your system just as you are able to do it from the input-output representation. Now, why would you bother to use this description when you already know how to use this description? Well, there are many methods for estimation and control that are designed to work with the state space representation of systems and are not directly applicable to the input-output relationship. For example, the extended Kalman filters that most of you have in the GPS software in your mobile phones are specifically designed to be used with the state space representation. And there are many other methods that require this form of system description, therefore you need to understand it and be able to construct it. So let's take a closer look at this state space representation. Very often we express the state space representation in a matrix form. This system of equations can be expressed in the matrix form like this. Here you can see that I have separated the state variables, the velocity and the position, and the external force, which I will consider to be the input to my system. Concisely, we can write it like this. This x is the vector of state variables, and we call it the state vector. This matrix A, which is this matrix, we call the state matrix or system matrix. The system matrix tells you how the current state will contribute to the change of the current state of the system. Now, this vector u we call the input vector, and in our example it is just a single element vector that contains the external force. In general, we can have multiple inputs, in which case this input vector would have multiple elements. And this matrix B we call the input matrix, and the input matrix tells us how the input vector contributes to the change of the system's state. And this entire equation we call the state equation. Now, it often happens that we are able to describe the behavior of our system like this, but we do not actually observe all the state variables of the system. For example, in the case of this ball on a spring, you could have a camera and you could use its image to measure the position of the ball, but you would not have any gauge that would measure the velocity of the ball. To describe this situation, we need to use yet another equation that will describe the relationship between the state variables and the quantities that we actually measure as the output of our system. In general, this equation can have this form, where the output, which in general can be a vector, is given as the function of the state vector and the input vector. These matrices are called the output matrix and the feed-through matrix. This entire equation we call the output equation, and in the case of our example, it would look like this. The output vector would have only a single element, which would be the position of our ball. This would be the output matrix, and this would be the feed-through matrix. So the state space representation can be expressed by these two equations, the state equation and the output equation. This is a fairly general form, but you can make it even more general. That even more general form is this, where the change in the state vector is given as some generic function f of the state vector and the input vector, and the output vector is given by some generic function g of the state vector and the input vector. This form is rather hard to analyze though, so you will be seeing this form much more often. Now let's learn some basic stuff about this state space representation. First, the schematic. This is the schematic of the state space description in the matrix form. To draw it, it is best to start with the relationship between the derivative of the state vector and the state vector itself. When the derivative of the state vector is integrated, we get the state vector itself. When we have this core part established, we can fill in the rest based on these equations. The derivative of the state vector is given as the state vector times the system matrix A plus the input vector times the input matrix B. And that is what I have here. The state vector derivative is given as the state vector times the system matrix A plus the input vector times the input matrix B. The output is given as the state vector times the output matrix C plus the input vector times the feed-through matrix D. The output vector is given as the state vector times the output matrix C plus the input vector times the feed-through matrix D. What does this look like in the Laplace domain? The Laplace transform of this is this. This derivative will become this multiplication by S. And the schematic is this. Now, what if I expand the matrix form into the individual equations? This is a case of the second order single input, single output system. When I denote the elements of the individual vectors and matrices like this, the state space equations can be written like this. And when I want to draw the schematic or block diagram of these equations, I can do it in the following manner. First, I will put down the relationship between the derivatives of the state variables and the state variables themselves. When the derivative of x1 is integrated, I will get x1. When the derivative of x2 is integrated, I will get x2. Now that I have this core part established, I will fill in the rest using these equations. The derivative of x1 is a11 times x1 plus a12 times x2 plus b1 times u of t. And I have it here. The derivative of x1 is a11 times x1 plus a12 times x2 plus b1 times u of t. Next, the derivative of x2 is a21 times x1 plus a22 times x2 plus b2 times u. And I have it here. The derivative of x2 is a21 times x1 plus a22 times x2 plus b2 times u. Last, the output is c1 times x1 plus c2 times x2 plus d times the input. The output is c1 times x1 plus c2 times x2 plus d times the input. And this is your schematic or block diagram of a state space description of a second order single input, single output system. You also need to learn how to transform the input-output description into the state space description and vice versa. So if you have an input-output description of your system and you want to turn it into the state space description, this is what you need to do. In this input-output description, u of t is the input and y of t is the output. Now, I will denote y of t as my first state variable, and I will denote the derivative of y of t as my second state variable. And these two guys will give me my state vector. Moreover, when I substitute this equation into this one, I will get this expression, which I can use as the first state equation. To get the second state equation, I will take these equations, substitute them into my input-output relationship, which will give me this, and from here I will express the derivative of the second state variable, which will give me this. And this is my second state equation. Check it out. My first state equation tells me how my first state variable changes, and my second state equation tells me how my second state variable changes. Now, if I need it, I can put these two equations into this matrix form. Last, I need to express the relationship between the state variables and my output y of t. For that, I can use this very first substitution that can also serve as my output equation. When I express this equation in the matrix form, I will get this. So this is how I can get the state space description of a system from the input-output description. In practice, it may happen that you have this input-output description, but you need to extract these matrices to construct some controller of your system. In that case, you need to be able to do this. Now the opposite direction. This can be done in time domain if your output is one of the state variables. Basically, all you need to do is to substitute the output for the respective state variable so that this state variable will no longer be present in these equations. Next, you need to express the remaining state variable from the equation where that remaining state variable is not differentiated. That is, you need to use this equation, not this one. Then you substitute to the other equation, which will eliminate you the second state variable, and you will be left with one equation that will contain only the input signal and the output signal. Thus, you will be left with the input-output relationship. When you do not observe one of the state variables directly, the computation in time domain is not so simple, but you can do it in the Laplace domain. This is the state space description of a single input, single output system in the Laplace domain. When you want to get the input-output relationship, you need to express the state vector from the first equation, which is this, and then you need to substitute it into the second equation, which will give you this. And here you get a familiar expression where the Laplace image of the output is given as the Laplace image of the input multiplied by some function of s. This function of s is of course the transfer function. So this is how you get your transfer function from the state space matrices A, B, C, and D. Now the transfer function can be written in the form of a rational polynomial function like this one. And these A and B constants correspond to these A and B constants in your differential equation, which is the input-output relationship. So this is how you would get the input-output relationship out of a general single input, single output state space representation. Moreover, for those of you who have heard about linear algebra, there is one more piece of information to be found here. In the transfer function, in this transfer function, I can express this matrix inverse as 1 over the determinant of this matrix times the matrix of cofactors. Now, these cofactors will have only positive powers of s, so they will contribute only to this polynomial in the numerator. It will be only this determinant that will create this denominator. Consequently, the poles will be given as the values of s for which this denominator is 0. Therefore, the poles will be at the values of s where this determinant is 0. And those values of s we call the eigenvalues of matrix A. So the poles of the system will be given by the eigenvalues of the system matrix A, and the system will be stable if these eigenvalues have negative real part. If you have never heard about cofactors and eigenvalues, then you should be worried, but not in this subject because we will not use this. In discrete time, the state space equations look like this. The next value of the state vector is computed from the current state vector and the input vector using the state matrix and the input matrix. The output vector is computed from the state vector and the input vector using the output matrix and the feed-through matrix. When you apply the z-transform, you will get this state space representation in the z-domain. The positive time shift will become this multiplication by z. These are the schematics, and they are quite similar to what we had for the continuous time. In time domain, you first need to write the relationship between the time-shifted state vector and the current time state vector. And then you complete the rest using these equations. The schematic in the z domain is equivalent, except instead of the time delay, you will have multiplication by the z to the minus 1, and instead of time domain signals, you have their z images.